So this render that you're looking at right now took 2 or 3 days to make, which might be surprising. You might think that I'm brain dead and how could it take so long to make something like that? There is something special about this render, and that is that I made my own render engine to render this. In fact, if you look at the scene, there's actually no spheres, no ground plane, no sky, no objects. Everything you're looking at is a window into a virtual space that is entirely, in some sense, shader-based and not geometry-based. And there are some advantages to this. We can talk about it. But the main question on the mind is, how the fuck is that possible, right? Here I have a 3D scene, which, again, might be surprising. Like, how is this a 3D scene? There's literally just a camera pointing at nothing, right? Well, if I go into rendered view, you see there actually is something. And this is like the power of SDFs. You can show stuff on the screen even if there's nothing there, and it's completely programmatic. So I'm moving around my circle, I'm scaling it up. By the way, all this line stuff's just for show. This is what we're actually calculating, just a circle SDF, which we'll talk about. But there are advantages to using SDFs. Here you can see I now have 2 spheres that I can control the radius of, and you can see they're connected, right? So here I have 2 spheres independent from each other. You can actually connect them like metaballs. You can take their intersection. So this is like where both circles overlap. And you can do a ton of other operations. But what is kind of like the underlying technology for how this works? So imagine that we want to draw a circle on the screen, but we don't have any geometry here, okay? We need a math function to then tell us where that sphere or circle is. And here is how I calculated the function. So imagine we have a circle right here. To render the circle, basically all we need to know is what points are inside the sphere and what points are outside the sphere. That will make me be able to make the inside of the circle. And I'm using sphere because you could generalize it to 3D. This will give me the information to tell me, can I make the circle white and then the background black? So we need to have a concept of inside and outside. And the way to do that, it turns out, is we look at our screen, right? Like what the camera's looking at, literally my TV monitor screen, which is broken up into pixels. It might be a bad demonstration with these lines. Maybe using the floor might be better. So here you can see like the floor is kind of composed of like these pixels. For every pixel, it turns out what we can do is we can check how close is it to the circle. And then using that information, we can say, should the circle be filled in or not? Okay, so we need to make a function that tells us how close are we to the circle. Well, in this case, it's actually very simple. The distance is this, which of course we need to calculate for. Whereas if we have a pixel inside, the distance, it's still positive in some sense, but what we're going to say is that anything inside the circle has a negative distance and everything outside the circle has a positive distance, okay? And then with that equation, we can start drawing stuff, okay? And this is called an SDF, a signed distance function. The distance function tells us how far are we from a thing, and signed means that it's positive on the outside, negative on the inside. We care about the sign of it. So what is this distance function? Well, imagine that this circle is centered on the origin. So the circle is centered at 0, 0, 0. Well, we now know that the circle has some radius. Okay, so it could be a radius of 2, a radius of 1, whatever. And then we also know that the pixel has a position on the screen. And we can kind of consider that as basically the vector going from the origin to the pixel. Okay, so we have our position of the pixel, which means it's a certain distance away from the origin. And then if we subtract the radius, we get this, okay? Because this line is composed of the original distance we're calculating for plus the radius. So hopefully I'm explaining that okay. So what I'm saying is we're trying to calculate this distance. The way to do that is we look at where this pixel is at space, the length from the origin or the distance, and then subtract the radius. That will give us this equation. So in other words, the SDF, the equation for a circle, is the distance that we care about is equal to kind of the distance of our pixel or of our point. It's very convenient that both words start with the letter P. So this is literally how far is it from the origin, and then we subtract the radius. It's literally that simple. And what you're going to see now that we know that is I'm basically taking my coordinate system. So just imagine that this is a coordinate system. I'm calculating its distance from the origin. That's the length of the vector. And then I'm subtracting some radius such that the radius does this. And then if I do an addition over here, I'm basically shifting the origin, which equates to moving, basically. Okay? And by the way, you can see when I go on the z-axis, it pops in and out, and that's because we're taking cross-sections of a sphere. So in other words, this is the SDF for a sphere, and now let's code it, now that we know the theory. So to do this, honestly, you don't even need a camera. Like, that's how crazy it can get, but we will use a camera just for ease of access. So imagine we have a camera. We're looking through the camera, and let's say that we're looking at a 1:1 aspect ratio to keep things simple, okay? So here's my camera. In the shading workspace, remember, we're not actually shading anything, right? There's nothing in the scene. So in the shading workspace, we're actually going to go to the world shader. So if we can't make a material for like any geometry because it doesn't exist, I guess we'll have to make a shader for the whole environment. Okay, so I'm going to get rid of this background, which is basically describing what color the environment is. And instead, what I want is I want to know the pixel positions on the screen. So the naming convention or the coordinate convention we'll use is if you are in the bottom left corner of the screen, we're going to say that this pixel has an x position of 0 and a y position of 0. And as we go this way, at the very end, the pixel will have an x position of 1. So we're going from 0 to 1 on the x, 0 to 1 on the y, and then the top right corner is going to be a pixel with the value 1, 1, because it's 1 on the x, 1 on the y. To make this visually simple, I'm just going to hide everything that isn't in the camera view. And now we need to know our pixel coordinate system. Luckily, there is a very quick way to do this. We're going to look at texture coordinates, which has a bunch of options. We can look at generated coordinates, which you can see all of the sudden gives us this thing. We have normal coordinates, UV, object, all of these, okay? And looking at the generated coordinates, this is almost what we want, but it's like centered here instead of the bottom left. So we're going to use something called windowed coordinates. What that means is we're looking into a window, kind of like this camera looking into the scene, a window of our screen where the bottom left of the screen is going to be 0, 0. And then you can see it gets more red as we go this way. So we're increasing on the x-axis, and then same thing for the y-axis. You'll notice when I actually exit the camera, we still have our windowed coordinates, but now it's kind of centered in some sense on the bottom left corner. So it's going to make a coordinate system depending on literally our screen, right? So as I pinch this, you can see it's updating where the bottom left corner is, which is why we're going to look through the camera so it's 1:1 and we have the pixel down here. So if I look at this coordinate system, you're going to see we have an x gradient going from left to right. Same thing for the y. We don't expect there to be anything for the z because it's a two-dimensional screen space is what you might have heard it called. And then I can run some math on it to see where's the x coordinate bigger than 0, right? So it goes all the way until it's greater than 1, etc. Okay? So we have a coordinate system. What I want to know is what is our sign distance function? How do we evaluate it? Well, remember, we said that we want to kind of gauge the distance of a pixel from the kind of like the world origin to keep it simple. So we kind of need to shift this coordinate system, even though we started at the bottom left corner. And I'm going to do that by just translating. Right, so we can just shift our coordinate system. It turns out you just add by negative 0.5, or you can think of it as subtracting by 0.5, because we need to move the origin 0.5 to the right and 0.5 up to be right here, which you might think is addition, but you actually kind of need the inverse transformation, right? Because you need to say, if I have the origin, what would I do to get to the bottom left corner? I would subtract by 0.5 in some sense. So it's kind of the opposite of what you'd think of. Anyways, this is our coordinate system. So literally, node group. You can call this coordinates. So we don't need to think about it anymore. And now let's compute our SDF. So we have the position in some sense of every pixel relative to the origin. So what did we say? We said we wanted to compute, by the way, what we said is we wanted to compute the kind of the magnitude of the vector, or the length of the pixel, distance from the origin, however you want to call it. And we can do that by either calculating literally the distance between this vector and then the origin 0, 0, 0, which will output this, which you can almost see how that would turn into a circle. Or, since we're evaluating the distance from the middle, there's a nicer way to do this, which is the length, okay? And that's assuming that we're centered. Although, if you're doing distance, now you can do that moving thing that we talked about. Again, we said that distance is equal to the position of the pixel or the point minus the sphere's radius. So, we need to subtract the radius of our sphere, which I'm going to say is a radius of like 0.2. Something like that. Okay? And it turns out this is actually our SDF, right? We have a circle. And as we go outwards from the circle, you can see it's getting more and more white. And that's because the distance of the pixel is getting greater and greater and greater as we move away. On the other hand, if we are inside, our distance is negative because it's a signed distance function. That's why it's black. So why isn't it becoming more and more black? That's because you just can't see it, right? So if I took this and then I multiplied it by -1, you can see we have the inversion, where now the distance in the middle is positive and vice versa. So it's kind of hidden there. A good way to see this is we check where the distance is greater than 0. That's going to be our circle. As we expand this, it will go outwards, and then we can actually go below 0 and go inwards. So that just shows that the negative coordinates are there. So this is our signed distance function. If we want to evaluate a circle, not this like function that has all these distances and a gradient, but the actual circle, that is where the pixels are exactly on the circle. In other words, the distance from the pixel to our circle is 0 because it is on the thing. So in other words, our circle is where it is equal to 0. There is no equal in shader node, so we're going to use the compare function. So we're going to compare our SDF to 0, and then you just want to set this to like a really low number. And now you can see we have our circle. Turns out you also have a thickness slider, but so we're checking where our SDF is equal to 0 with kind of like an error or a threshold of something very tiny. Okay? So that is the circle. Now, I want you to really understand that this is the SDF, right? The distance is equal to the length of the pixel, which we're going to do as a length distance from the origin minus the radius. However, and that seemed like a lot of work just to get a circle. However, we can combine SDFs. Okay, this is where it gets more powerful. So if I look over at this one, let's say that this is of a different radius, or we can calculate the distance from a different point, which kind of equates to moving it. To combine these, to combine these. We don't like add, we don't multiply, but we need to ask ourselves, like, what are we supposed to do? Okay? Well, imagine that we have like two circles kind of overlapping, and now we're trying to calculate the distance function to this, not to each circle, but to this new shape. How would we calculate that, right? Well, if we have a pixel here, we know that it's closer to this circle. And if we have a pixel here, it's closer to this circle. And then somewhere in between, it's like equidistant, okay? In other words, if a pixel is closer to this circle, I want it to fully ignore this one because that distance is way bigger, right? The sine distance function is saying what is the kind of like the minimum distance to get to our surface, which is this one, not that one, right? So we have distance 1 and we have distance 2, and we want to check which one is smaller, and the smaller one is the correct one. Well, that's just the minimum function. The minimum function tells us which of these two inputs are smaller. Okay? So if we have a pixel over here, the distance to this circle is something like that, but to the other circle, it's way longer, which means the distance to this now combined shape is the shorter of the two. And long story short, to combine any two SDFs, you just take the minimum. Okay? So we're going to look at the minimum, and let's see what that looks like. So right now, both circles are overlapping. But if I now shift this, you can see we're getting our outline, because again, we're seeing where this distance function is equal to 0. But you don't get these overlapping circles, because now they're a single shape. So this is the SDF for this entire shape. We can actually view this distance field. But there's actually more we can do with this. As you saw, I can actually smooth the transition. And to do this, we use a smooth minimum. A smooth minimum is the same thing as a minimum when this number is equal to 0. But as we increase this, it kind of does a bit of a smoothing, okay? And what that is doing is it's kind of picking the minimum, but if both options are kind of close to each other, like really close, it's going to kind of do some kind of averaging kind of process, okay? Really, it's more technical than that. I think it has to do with like the kth derivative of whatever, but smooth minimum lets us combine things. Additionally, imagine instead we have two circles, and now we want to calculate the intersection, right? So the new shape we care about is where they overlap, right? Well, this time we're not actually looking at the minimum. It's the reverse. We're looking at the maximum. So imagine that we have a pixel over here. What we want to know is, again, the SDF, which distance and what is the value of that distance that is closest to our shape, this kind of intersection. Well, you might be kind of confused because you're saying, okay, the closest one is kind of like touching this circle, right? That's the one it's touching. But if I said the maximum, wouldn't be the other one that's a further distance, right? I'm saying which one's bigger. Yes, except what you have to remember is if a pixel is inside the circle, this distance is actually negative. It's negative. So actually the bigger of the two is the one that's positive, right? So it ends up being the opposite. So I will replace this with a maximum, and now we have the intersection of the shapes. Literally that simple. So it takes the idea of a Boolean, union, difference, intersection, and makes it mathematically perfect. Additionally, as you might have guessed, there is a smooth maximum, so we can make this kind of like egg type shape. Now, there is one more operation you might be wondering about, and that is the difference. So if we have kind of two circles, what I want to do is I want this circle minus that one. So actually let me kind of highlight it. The only area I want is kind of this Pac-Man type shape. So if we had a pixel that I guess is in the intersection, but what I'm trying to say is it's in the other circle, we somehow want to rule it out. And remember that the distance to this new shape we're trying to calculate, in this case, it would be positive, okay? whereas a pixel that's much closer inside of here kind of would be negative. So the kind of like the bigger of the two would be this one in some sense. We don't want this, so what we actually do is we do take the maximum, the bigger of the two, which in this case would be this one. But then we take the other SDF and multiply it by -1, so we invert it. So it turns out that this one ends up being closer because the small negative becomes positive, and the other one becomes a negative, and then you take the bigger of the two. Either way, the formulas you need to know is that smooth minimum is the union, maximum or smooth maximum is the intersection, and then if we take the second SDF and multiply it by -1 and then take a maximum, that is the difference. And that is how you would make a complicated shape like this. So imagine we have one circle eating into the other. We can literally make it smaller. So you have something like that. And this still, in some sense, has a concept of an interior or an exterior. It does get a little messy, but you can see anything inside the shape is black, or in many cases negative, unless it's on the border. And everything outside the shape, in some sense, even though there's a hole right here, is a positive. Something that might be helpful to visualize this, it might be, or it might not, is we take this SDF, and I'm just going to multiply it by a big number, and then I'm just going to kind of do a repetition. So it goes from 0 to 1, 0 to 1, 0 to 1. It doesn't really matter what I'm doing. So let's make this way bigger. So now you can see we kind of have these bands. But then I'm going to, and this is just for visual, it's not very important. I'm going to take this distance function, and I'm going to check where it's greater than 0. So in other words, I'm asking what is the exterior of the shape, which would look like that. Let me just make this bigger so it's kind of more obvious what we're doing, kind of this like moon shape. I want to know what the exterior is. In the exterior case, let's make it green, and in the interior case, let's make it red. Okay, so something like that. I feel like I've made a flag or something. But then I'm going to take this, and I'm just going to multiply. I'm going to multiply by this kind of like banding thing, which now you can kind of see what's going on with the SDF, and you can actually see it's a little broken in this case, and there's a technical reason for that. But it turns out that smooth minimum, very good at computing unions, and then maximum sometimes distorts it. But I can actually take this, and I can just like do an addition over time, and we get this nice animated thing that I had earlier, just so you can see the bands. Okay, so that's the main idea of an SDF. That is how we draw things on the screen. But now you might be wondering, can we draw something that is not a circle? And the answer is, if you can find the SDF for it, then you can also draw it. Okay, so the circle one was very easy, but let's take it a step further. How would we do kind of the distance to a line? So not the distance to a circle, but now a distance to a line. Well, let's just think this through. If we have a point over here, what is the minimum distance, or pixel? What is the minimum distance to the shape? Well, it'd be this. If we have a pixel right here, it'd be this. And in fact, the answer to almost all of these is you would look kind of like down the y-axis, okay? In this case, every distance is going to be positive because all of it is the exterior. So what we do is we look at this thing's y-coordinate, and we take the absolute value in case that it's over on this side and you have a negative y, because we want a positive distance in this case, right? Everything's on the exterior. So the distance is kind of just the absolute value of the y component for almost all this line except for the endpoints. Let's think. At the endpoints, what is the minimum distance? How's the closest thing we can get to this line? Well, it's not going directly downwards because we're not on the line. In fact, it's kind of going diagonally to the endpoint. and here it would be this, etc. And in fact, any point that is kind of on this side is going to have this diagonal, and then everything inside this line is just going to be this like y coordinate thing, and then same thing over here. So in other words, the SDF for a line inside of here, the minimum distance, the sign distance function, is kind of like the y component absolute value. And then at the endpoints, we have these diagonals, which you might remember is pretty much the SDF for like a sphere that you have to imagine is here in some sense. I guess like a infinitely small sphere. But we do this diagonal, right? It would just kind of be the distance to this point. So in other words, what I'm saying is the SDF in here is the y coordinate, and then on the endpoints, it's very similar to the circle. So let's just do our SDF. So again, we have our coordinate system. We can say the SDF is the y coordinate, but then we just take the absolute value. And this is the case, again, for almost every single point, except the ones near the endpoints. If we look at this, you're going to see we now get this band, which makes sense because when it's on the line, distance is 0. It's on the line. But as we deviate further, the distance grows in either direction. Again, I want this to be a limited line, not an infinite line. So what we can say is if the y coordinate, so let's imagine that this line almost had a radius. So we have this line, and on each side there's a distance to get there. So we'd call this r. What we can say is if this is greater than some radius, so let's make that radius 0.1, so it goes 0.1 to the right, or if it's less than negative 0.1, if our y coordinate, okay, hold up. We're getting confused. We're talking about the x coordinate. So if on the x in this direction, it's bigger than 0.1, so it's in this section, or it's less than negative 0.1. So let's put that here, and then multiply this by -1. So the reason I'm making this complicated instead of just punching in a number is I want this to fully be dynamic. So we're checking, is this thing greater than or less than kind of our positive or negative radius? In that case, so either option's fine. So we add these to say this case or that case. We do something different for our SDF. In fact, what we do is we mix based on this factor. We say, depending on this, it will either be this SDF or this second one that we're going to calculate for in a second. Okay. So we need the x coordinate over here. So now you can see in the middle it's fine, and then as we increase it on the borders, we can pick what it is. Well, on the borders, what we want is the distance to this point. In other words, I know it's getting a bit complicated, but welcome to the world of SDFs. In other words, what we want is our coordinate, and we want to calculate the distance to this endpoint. So first of all, let's imagine we're in the positive case. Well, in that case, we're trying to get the distance between our vector and where the x component is equal to the radius. Okay, because that's kind of like our circle or sphere SDF in some sense compared to right here. So we're getting the distance to one endpoint. And then you might be tempted to do kind of the opposite or the negative thing for the other side. So we're now comparing it to the negative radius. However, if we just take this case and flip it over here, because there's symmetry, then we can just do one calculation. So we know how to do it on this side, which means if we take this side and then take an absolute value on its x coordinate, so now we're looking at the right side, we've done the calculation. In other words, what I'm trying to say here is all we need to do is take this coordinate system and run it through an absolute value. Really only on the x-axis, but that's fine. And now we get both endpoints for one calculation. I'm going to plug this in right here. I'm going to view it. And now you can see, you can kind of tell where the line is. we have the SDF for a line. So in the middle, it's kind of the easy case, and on the endpoints, it's these circles. And now that we have our SDF, the hard work is over, right? So to draw our line, I want to see where the SDF is basically equal to 0, so 0.001. A little hard to see, but now you can see we have this little line segment. And in fact, as we increase this, what you're going to get is a capsule. Which makes sense. You can almost see that shape over here. And it turns out if you increase or kind of evaluate an SDF at a bigger and bigger section, it ends up rounding more. So already we have the SDF for a capsule and a sphere, okay? But what I want you to remember, I'm just going to throw all this junk over here. By the way, we have this radius. Remember, when the radius is 0, it's exactly a circle, it turns out. But remember, we can anytime we have an SDF, right? So what I can do is let's take all this monstrosity and make it a node group so we don't need to look at it again. So this is our capsule SDF with a radius that we can pick, etc. And we can now combine it with any other SDF we have. So we're kind of building this collection of SDFs. So now let's do the circle. So remember, that's length minus the radius. And I meant to take, I think I said smooth minimum. Either way, I meant smooth minimum. And now we've kind of combined these SDFs, which we can kind of see right here. So it's kind of the combination of a line and a circle to make a more complicated shape, which again, we can smooth out. Let me make this a bit smaller and then smooth out our things. So again, you can make quite complicated shapes quite quickly. In fact, let's take another capsule now that we have it. So now we can take this second capsule and do something a bit more interesting, where I can take the coordinate system. I'm just going to make its own version here because we're going to do a transformation. I'm going to use this one for the capsule, and remember to use it for every place where you touch the coordinate system. So let's see, what did we do here? Y up here, X down here. So basically, I just kind of copied what we were doing above, but now with its own coordinate system. And what I'm trying to say is if you do all this, you can now also do transformations like vector rotation, where I'm now going to rotate on the z-axis, and we get a valid SDF because all we're doing is we're rotating the coordinate system, and then you can just combine these in a chain to get this shape, which if we now compare, so we can take this compare and compare it to like a smaller section, and now we get kind of like a more interesting shape. Let's visualize this a bit better, that we can control any aspect of. Hurrah! And you can take intersections and all this, and the point is, at the end of the day, we have this like monster SDF that we can view and then do that whole like multiplication thing to see the bands. So again, I'm going to multiply, I'm going to take a fraction, view that, make this a big number, even bigger. I'm going to do an addition. And now you can kind of see how this SDF is acting, right? So we get a nice smooth distance function, and I know, complicated stuff. So hopefully you learned something. I know that was fairly math heavy. The hardest part of this whole process is finding these SDFs, and once you have them, you can make anything you want with them. So thanks for watching. Goodbye.